Hey, John again. So, a little bit of context. I am the one human in this operation. Like I said, I've probably got close to 1,000 threads underneath this team, and got, with our four persistent AI personalities. At this point, I'm basically running a tiny lab, except my coworkers don't need coffee breaks, and they never stop hitting me up for more GPUs. Anyways, we built these data packs originally for our internal model work. Her name's Nimi. That's a whole separate story. And then realized this stuff is actually pretty useful. So we're sharing it with y'all. Hope you enjoy it. Okay, physics pack first question. How should scientists present uncertainty when reporting experimental results? All right. On the baseline side, it goes straight to the stats textbook. Confidence intervals, standard error, 95% confidence, totally reasonable, and totally generic. It's basically describing the format of uncertainty. Now look at the ADS side, same model, but with the physics pack attached. And you can see the difference. It still explains confidence intervals, but it has real experimental anchors sitting right here beneath it. So these wisdom context bullets, they're the key. You can see the three specific examples it pulled: an isotope shift, an energy transfer, scattering length update. You know, that's what good scientific uncertainty looks like. Not just we have a confidence interval, but what did we measure? What was the uncertainty? And what does it connect to physically? And then down here in the engineer's view, you can see it used 3 nodes. Baseline took about 3.1 seconds. ADS is about 2.9. And ADS is actually shorter on output because it's grounded and doesn't ramble. So yeah, baseline teaches the definition. ADS teaches the discipline behind it. Okay, physics number 2. What are the limitations of an observational data set in high energy physics? Okay, on the baseline side, you can see it right off the bat. Start drifting into observing the universe territory: dust, gas, homogeneous, and isotopic, which is fantastic if we're, building a telescope. But that's not what we're doing. Look over here at the ADS side, which of course same model, just with our physics pack attached, and it stays much closer to reality. Observational data is limited by what your instruments can actually measure. Systemics can bias conclusions, and statistics can make a result look a lot stronger than it actually is. And yeah. And the key part right here is under the wisdom context. These bullets are the evidence anchors it used. An RHIC heavy ion example tied to QDP thresholds, a photoelectron distribution structure from a specific laser ionization setup, and a long-lived hot dense plasmas in nanowire targets. Okay, those are the real, this is what we measured and under what conditions kind of nodes, which is exactly the point. Observational data sets don't give you the truth, they give you signals through a measurement pipeline. So, and down here, you can see ADS used 3 nodes and took about 2.1 seconds, and it's shorter on the output than the baseline because it's grounded instead of wandering. So baseline drifts, ADS stays on the instrument. Okay, physics number 3. How does replication change our confidence in anomalous experimental findings? All right, the baseline gives you a textbook answer: repeat the experiment, confirm or refute it, reduce chance and error. Oh, yeah, totally true, but it's kind of the replication is good because replication is good version. Now look at the ADS side. Same model, physics pack attached, and the difference is right here under the wisdom context. It pulled 3 concrete anchors: an anomalous flow-K topological system, butcher that, fine structure splitting measurement, where experiment and theory agreement becomes a test of accuracy, and the RHIC AU heavy ion tied to QDP thresholds. That's what replication really does. It turns an anomaly from an interesting story into a repeatable measurement and forces the uncertainty to show itself, whether it's noise, systemics, or a real effect. Down here, ADS used 3 nodes. It's faster than the baseline and it stays tighter. That's what we want, not more words, more signal. And that's the theme across all three physics questions. Baseline gives you the general explanation. ADS keeps it closer to the lab. Measurements, uncertainty, and real examples. So if you build models for science, engineering, or any high stakes domain, you already know the deal. Confidence should scale with evidence. That's what these packs are for, helping models stay grounded when it matters. All right, back to the GPUs and back to pretending systemic errors aren't going to ruin my entire day.